In the last video, we gave kind of a general overview of hyperbolic functions and what they were and what they were used for and that sort of thing. This video is going to be a continuation of that last video where we're going to look a little bit more specifically at the individual hyperbolic functions. So here's the first three: hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. These three guys are defined a certain way. And the one thing I'll stress over and over in this video is that these guys, even though they look like trig functions, they are not trig functions. They're not periodic. They don't oscillate back and forth. They don't do the sorts of things that we'd expect trig functions to do. There is a reason that they closely resemble trig functions, but they're not trig functions. So here's our first three. Here's how they're defined. Hyperbolic sine is defined as e to the x minus e to the negative x over 2. Hyperbolic cosine is defined as e to the x plus e to the negative x over 2. And then hyperbolic tangent is defined as hyperbolic sine divided by hyperbolic cosine. There are also three others. Here's the other three. There's hyperbolic cosecant, secant, and cotangent. And as their trig counterparts, they're the reciprocal of sine, cosine, and tangent. Hyperbolic cosecant is 1 over sine. Hyperbolic secant is 1 over hyperbolic cosine. Hyperbolic cotangent is the reciprocal of hyperbolic tangent. So all of these guys can be based off of the original hyperbolic sine and hyperbolic cosine, which were defined in terms of this exponential function e to the x and e to the negative x. All right, so let's look at these one at a time. That's going to be our main goal for this video, is to look at all six, see what they look like, see what their graphs look like, all that sort of stuff. There's 6 of them, so to keep this short, I'm going to go into a little bit of detail for hyperbolic sine and cosine, and then for the other 4, we're just going to breeze through those, and I've already written them on the cards just to kind of speed things along. All right, so here we go. Hyperbolic sine. Well, what's this guy look like? Well, let's remember how he was defined as e to the x minus e to the negative x all over 2. So let's just use a little bit of reasoning skills here to see if we can figure out what this guy looks like. All right, one general principle that we can stand on is as the x's get larger, we just know this from algebra, e to the negative x goes to 0, it converges to 0, because basically you're getting e to a large negative power, which would be equivalent to 1 over e to the large positive power, which is practically 0. So anyway, as the x's get larger and larger and larger this way, this term basically decays off, and we're roughly left with e to the x over 2. So what does that guy generically look like? At least on the right hand side, it looks something kind of like this. Okay, it kind of resembles e to the x, but dividing by 2 will flatten it out a little bit. Specifically at 0, we can at least do that exact value. E to the 0 is 1, e to the 0 is 1, 1 minus 1 is 0, 0 divided by 2 is 0. So it does go through the origin. All right, now how about on the left-hand side, kind of in this direction? Well, for the same reasons as before, this time e to the x will go away or disappear when you plug in a large negative exponent. So when this guy's gone, you roughly get negative e to the negative x over 2. So we know what e to the negative x looks like, but due to this negative, it's going to be reflected downwards or across the x-axis, and it'll be below the x-axis. So it'll look something kind of like this at the end of the day. So this is the graph of hyperbolic sine of x. You can verify this on your calculator. We might do that in one video. We might pull out the calculator and look at some of these guys. But keeping it short for this video, what's this guy's domain and range? Well, the domain would be all real numbers, so minus infinity to infinity. Why is the domain all real numbers? Well, look how hyperbolic sine's defined. He's defined in terms of e to the x and e to the minus x. There's never any x values ever that would make this expression mess up. You'll never get division by 0. You'll never get a negative under a square root, or those typical places that functions often mess up. What's its range? Well, it looks like the y values go up and down for forever. So the range would also be minus infinity to infinity. So we did all that manually by hand. We constructed the graph and the domain and the range for the hyperbolic sine function. All right, let's do the same thing for hyperbolic cosine. This will be the last one we do by hand. Hyperbolic cosine is e to the x plus e to the negative x all over 2. And let's think about this guy logically. At 0, where are we? E to the 0 is 1, e to the 0 is 1, 1 plus 1 equals 2, 2 divided by 2 is 1. So it'll definitely go through this point right here. For the same logic as before, the larger the x's get, the e to the negative x decays off, and you get basically e to the x over 2. So the right hand side looks very similar to this guy's right hand side. So let me get rid of those. All right, we'll look something kind of like this. And on the left hand side of the y-axis for the large negative y's, again, e to the x will decay off, but notice there's a difference from the hyperbolic sine function. Remember how this wound up being negative due to the minus? Well, if that negative was a positive, it would be up in the air, not going down. So hyperbolic cosine will actually look something kind of like this. I briefly mentioned this in the last video. The shape that this guy makes is called a catenary. Catenary. We see a lot in engineering courses. If any rope or chain or anything of that nature hangs between two fixed points, think of like some chain hanging between two posts, between two railings or something. The shape that this makes is called a catenary, and it's modeled by the hyperbolic cosine function. The domain for this guy, just look at the green, you ignore the pink. The domain is all real numbers, so minus infinity to infinity. And the range looks like it starts at 1 and then all the y values above that. So from positive 1, inclusive rather, sorry about that, should be a bracket, from 1 to infinity, because we get all the y values above 1. All right, there's hyperbolic cosine. I could continue with similar logic for all of these, but just to speed things along now, I'm quickly go through the last 4. Here's hyperbolic tangent. If you kind of went through the logic of it, then you would see that his domain is all real numbers, because hyperbolic tangent being defined as hyperbolic sine divided by hyperbolic cosine. You'll notice that hyperbolic cosine is never equal to 0. It's never 0. You see the hyperbolic cosine graph never crosses the x-axis, which means hyperbolic tangent never gets in trouble. And so his domain is all real numbers, and the range is minus 1 to 1. All right, so it kind of looks like this. So you have horizontal asymptotes at y equals negative 1 and y equals 1. Hyperbolic cosecant looks something like this. Its domain is all real numbers except for 0. There's a vertical asymptote. And the range is all real numbers other than 0. You have a horizontal asymptote at y equals 0. Hyperbolic secant, this is an interesting looking graph. It comes up and it kind of just has a little blip or a little bump right here at the y-axis, so y value of 1, and then kind of flattens out on both sides. It has a horizontal asymptote at y equals 0, or the x-axis. And lastly, hyperbolic cotangent. You work through some of that logic, you would see this is the graph you get. His domain is all real numbers except for 0, because you get a vertical asymptote at the y-axis. And his range is anything above 1 or below negative 1, not inclusive. So anyway, I know that's kind of boring and dry a little bit, but it's important to know what these guys' graphs look like, if we're going to use them for anything. Okay, so there's a little bit left we have to talk about. That's just kind of a light introduction to what the graphs of these guys look like and what their domains and ranges are. In the next video, we're going to look at some identities that these guys have. You remember from your pre-cal class, there was a gazillion trig identities, most notably like sine squared plus cosine squared equals 1. That's the one that everybody knows. And there are a bunch of others as well. Well, there turns out there's a lot of hyperbolic identities as well that closely mirror those trig identities. So we're going to look at those in the upcoming video.